Okay, in part 3 of lecture 17, we are going to learn about the second type of the filter, which is a high-pass filter. So, as what we have seen in the first type, which is a low-pass filter, we have a case whereby the filter shall permit, shall permit a frequencies which is lower than the cutoff and stop a frequency which is higher than the cutoff. That's for the low-pass filter. So for the high-pass filter, it's the other way around, yeah. So it will then cut a frequencies lower than the cutoff, and it will permit a frequency which is higher than the cutoff. So this is the ideal case, yeah, the ideal magnitude plot for the high pass filter, a stop band for a frequency lower than the cutoff, and pass band for a frequency higher than the cutoff, yeah, right. So again, there should be two types of the high pass filter, which is the RC circuit and also the RL circuit. So looking at this, we can say that the minimum order for the high pass filter will be a single or first order of the filter. Yeah, because we only have a single reactive components for both RC and RL circuit. Yeah. Okay, so let's have a look on the first type of the filter. Okay, so this is for the RC circuit. So if you can recall back for the RC circuit for low pass filter previously, the output voltage is measured across the capacitor, yeah. But for the high pass filter type, for the same RC circuit, the output voltage is measured across the resistor. Okay, so that is why when we calculate the transfer function equation for the high pass filter for the circuit, it will be S over S plus 1 over RC. Okay, so looking at this transfer function, we can then deduce that for a high pass filter, there should only be also two components for the transfer function. The first component is a zero at origin, okay, and second component is a real pole value, okay. So it is different than what we have for the low pass filter before, because for a low pass filter, if you can recall back, the transfer function is consists of constant and real pole. But for the high pass filter, it consists of zero at origin and then a real pole value. Okay, so that should be the transfer function, yeah, for the high pass filters. Okay, so this should be the cutoff frequencies where we have 1 over RC, which is similar to what we have seen for the yeah, previous low pass filter cutoff frequencies, where we have 1 over RC. So again, by selecting R and C values, we can design the filter according to our specification. Yeah. All right. So basically, for this board plot, there should be zero at origin, and we have a real pole, and sometimes we can have also a constant. Yeah. So this will be the possible components that we're going to have in the board diagram for a high pass filter style. Yeah. Okay. So this will be the common board diagram for the high pass filter. Okay, which is against the plot that we have for the low pass filter before. Yeah. So we have the slope. This will be the cutoff. So this will be the stop band region. And then we have a constant amplitude. This will be the pass band region. Yeah. So we have a stop band region. We have a pass band region. Okay. And for the second types of the filter, where we have the RL circuit. So if you can recall back previously for the RL circuit of the high pass filter, the output voltage is measured across the resistor, yeah, for the low pass filter. So for the high pass filter is the other way around, where the output voltage is measured across the inductor L. Okay, so you can prove this on your own, that the transfer function for this kind of the filters where the output is measured across the inductor can be shown to be look like this, yeah, S divided by S plus R over L, yeah. So again, the cutoff frequencies for this filter will be R over L still, yeah, it should be the same as what we have seen before for the low pass filter. So again, we can design the filter according to our specification by simply change or choose the proper value of R and L, yeah, to give us the required cutoff frequencies value. Okay, so again, if you look at this transfer function, a common components for the high pass filter will be zeros at origin and a real pole, yeah. And sometimes we can also have a constant value, yeah, for to be part of your board, to be part of your transfer functions, yeah. Okay, so that should be the plot for transfer function, yeah. Okay, let's have a look at this example for the transfer function for a high pass filter. So we are given this transfer function with a 20s over s plus 10. We have to determine the type of the filter in the board plot, and then you have to determine the cutoff frequencies. So first thing first, we need to plot the board diagram. So let's have a look at the example for this solution for this example. HS will be 20s over 2 over s plus 10. Okay, so we are going to, okay, looking at this, again, we have three components. We have a constant of 20, we have a zeros at origin, and we have a pole at 10, yeah? So basically, we need to write the transfer function in this form, okay? So I think I've taught you how to uh, rearrange the transfer function, yeah, and write the equations in this form, yeah. So you don't have to do this again for these examples. You can prove this by referring back to lecture 16, yeah. So we're going to have these components where we have a constant of 2, we have zeros at origin, and we have poles at 10. So let's plot the board diagram for this transfer function. So we're going to have 20 log 2, yeah, 20 log 2. So that will give us approximately 6 dB amplitude. For the zeros at origin, we have S here. So zeros at origin, basically, we are going to have a slope of positive 20 dB per decade, where the slope will pass through the frequency of 1 radian per second at the horizontal axis. Okay, so that will be the plot for your zeros at origin. Whereas for the pole at 10, we are going to have a constant 0 dB amplitude up to 10 frequencies. And after 10, we are going to have a slope of negative 20 dB per decade. So these are individual slopes for a constant of 20 log 2, for zeros at origin, yeah, and also for a pole at 10. So these are the individual plot. So in order for us to obtain the final plot, yeah, so I think I've taught you in lecture 16. Okay, so we have a constant of 6 dB. So since we are using the starting frequencies is at 10 of negative 1, so this plot for zeros at origin will start at negative 20 dB. Yeah, because the slope will be 20 dB per decade. So because of the existence of this 6 dB as a constant, okay, the new plot or the final plot shall start at negative 14 dB. Yeah, because this is somehow related to the amplitude shifting. Yeah, so negative 20 due to 6 dB amplitude, the plot will start at negative 14 dB. So it will follow the plot, the slope of this initial plot of zeros at origin. So we're going to have the plot of positive 20 dB per decade, and it will then stop at 10 radian per second frequency. Because at 10 radian per second frequency, we are going to have two slopes. The first slope is 20 dB per decade positive, and the second slope is negative 20 dB per decade. So when we combine these two slopes, we are going to have a net slope of 0 dB per decade, and that's why we are going to have a constant amplitude here. Okay, so that should be the final plot. So the red line here is your final plot for the given transfer function. So looking at this final plot of the given transfer function, we can then state that this will be a plot for the high pass filter, where the slope, yeah, of positive 20 dB per decade for a frequency lower than 10 radian per second will be a stop band. And for a frequency bigger than 10 radian per second, which is a constant value, so this will be a pass band region. So we have a stop band region and we have a pass band region. Yeah. Okay. So this will be a high pass filter, and the cutoff frequencies we're going to estimate it to be around 10 radian per second. Yeah. So that should be your cutoff frequencies, because this is the region. This is the frequencies which separated the stop band and the pass band. Yeah. Okay. So hopefully you understand about this cut off, I mean, the board diagram for the given transfer function. Yeah. Okay. About the phase plot, I believe that you can try to find the phase plot for this transfer function. Yeah. Okay. So I'm going to stop here. So in part 4 of lecture 17, we're going to do few examples, yeah, related to this low pass filter and high pass filter. Okay. Thank you.